think we can probably we're just a couple minutes ahead, so let's just move on to the next talk. This is given by Sam Lawrence, who will talk about the Artemis science mission objectives. So Sam, please take it away.
So thanks very much. I'm delighted to be here today. The organizers of the meeting asked me to come in and give a brief rundown of the Artemis 3 Science Definition Team Report outcomes, specifically as they pertain to the topic of this workshop. And this is the most detailed mission planning for human beings on another world in 60 years. And so I'm very proud of the work we all did, and I'm delighted to share it with you all here again today in this context. Next slide, please. Okay, as a quick recap, the science definition team for Artemis 3 was chartered by Dr. Zurbuchen for the NASA Science Mission Director. The committee was charged with defining a compelling and executable set of science objectives for the Artemis 3 mission, the first human mission to the surface of the moon in the 21st century. And we were to assess the objectives for the mission to achieve the science goals articulated by NASA, including investigation approaches, key surface science activities, and potential inputs into the concept of operations. And then the outcome, of course, was a final report, which was submitted to the Planetary Science Division that contained a prioritized set of science objectives for all aspects of this Artemis 3 mission, including sampling strategies, science goals, priorities, deployable instrument packages, and feed forward to future Artemis base camp activities. Next slide, please. And as a reminder, there's the committee membership. So we had some of the very best scientists in the world. There were concerns at the time. The report was written about interfering with the competitive ongoing procurement of the human landing system. So we had to go with a civil servant only panel. But we have made significant investments in the civil service workforce over the past 10 years. So these were the very best scientists in the world doing this. And we also had a set of community consultants, Fagan, the league chair, Dr. Peters, of course, the Survey Distinguished Scientist, and Juliana Gross, the Captain Lunar Subcommittee Chair. And I'm really proud of the work that this group put into the report, and I wanted to specifically highlight the work that Renee Weber did leading the charge. Next slide, please. Okay, so the report is available still on the NASA website, and it's broken down into a very cohesive kind of way across 9 chapters and some references and some appendices. So the one we're going to focus in on here today is the Candidate Science Program, and very specifically Table 1, the Science Traceability Matrix. Next slide, please. Okay, so before the report was written, many of the same characters had gone through, just really dug down deep into 50 years of community documents describing follow-on science goals for post-Apollo missions, service missions to the moon. Most notably, the Advancing Science of the Moon report, produced by League in 2017, the Lunar Exploration Roadmap, the 2007 National Research Council report on the scientific context for the exploration of the moon, and of course the Visions and Voyages document. And it was very clear that the same themes just kept on coming over and over again. They are understand planetary processes, things like impact cratering, understand the character and origin of lunar volatiles. That's essential for science, understanding the volatile inventory of the solar system, but also very important for developing a cislunar economy, interpreting the impact history of the Earth-Moon system, revealing the record of the ancient sun in our astronomical environment, observing the universe and the local space environment from the unique vantage point of the moon, conducting experimental science in the lunar environment, and then investigating and mitigating exploration risks to humans. So the XDT was charged with expanding upon the science that could be done to achieve these objectives. And so we chose to map the science goals, which were areas of research down to specific activities that were undertaken to address the goals. And those are all outlined in the Science Traceability Matrix, Table 1. Next slide, please. Okay, so Doctors Weber and Cohen and I have all shown this particular slide on many different occasions, so I don't want to spend too much time on it. But the traceability and prioritization drew heavily on the community submitted white papers that were submitted as part of the activity, as well as our guiding documents, several of which actually did offer time phasing and prioritization, especially the Lunar Exploration Roadmap. And each investigation was ranked on two independent criteria: compelling science, or how fundamental the investigation is to making a significant science advancement, or whether Artemis 3 presents an enabling opportunity given to the architectural constraints. And I will point out that the architectural constraints from the Science Definition Team report, very specifically highlighted there, remain, pretty, still exist today. So another subtle point about Table 2 I'd like to make is that it includes more objectives than could be accomplished on a single mission. So that is where the feed forward aspect of it to future sortie missions, possibly even extended surface activities at a potential Artemis base camp, what plays into it. Next slide, please. Okay, so we constructed a notional candidate science program that would capture the highest priority science for Artemis 3 and provide the greatest feed forward to follow-on missions. And it's a cohesive program containing a mix of sample collection and return, in-situ science and field science, and deployed experiments. And so that taken collectively, that candidate science program addresses the highest priority investigations and a multitude of other ones. Next slide, please. Okay, so the biggest takeaway from the report is how just the importance of sample return. So samples for Earth return address a wide range of investigations, not just those that were highly ranked. Samples are a resource that continues onward for years and years and years. So the committee recommended traditional sample collections like rake samples, as well as advanced techniques like hermetically sealed and possibly even cryogenically maintained regolith core samples to preserve volatiles in soils. But again, we're not presently planning on cryo for Artemis 3, but possibly for future missions. Continued investment in terrestrial laboratory facilities, analysis techniques, and the workforce required to sustain all of those are also needed to make the best use of the return samples. And then we highlighted a notional sample collection strategy. I will point out that this was accurate at the time it was written, but our understanding of both the sample, the mass collected on the surface, and the sample containers required to achieve those is constantly evolving. So I would focus more on the kinds of samples and the style of sampling than on the exact mass breakdowns. This particular table. Next slide, please. Okay, so on to today's topic. So 2 minutes remaining. I'll try to get through this as quickly as I can. So the down mass allocation for science and utilization must be first reserved for sample collection tools and sample return containers. So there may not be much mass available for in-situ tools, handled instruments, or crew deployed experiments left on the surface. Those have to be very high impact. And measurement techniques are preferred that maximize science return by addressing multiple investigations, but also possibly offer other benefits like increasing crew safety and reducing risk for future missions. And those are broken down into in-situ volatile monitoring, deployed environmental monitoring, geophysics investigations, in-situ geochemistry, mineralogy, geotechnical properties, and geophysics, of course. So let's run through this in a bit more detail. Next slide, please. So if you just jump to the executive summary of the report, as well as that was written, you're going to miss a lot of the subtle details contained in the text and the body of the report. So the ones that are most relevant for this workshop are section 6.3, pertaining to in-situ instrumentation. So in-situ instrumentation will be greatly beneficial in addressing a number of Artemis science investigations, including instrumentation to support sampling, volatile monitoring, geophysics objectives, downhole monitoring, and geotechnical characterization. So section 6.3.1 points out the advantages of sampling instrumentation to enhance samples, sample collection and curation. So in-situ instrumentation could be used for sample triage, additional contextual data, and increasing the variety of lunar locations that get sampled to some level, even if you don't bring samples back, as well as documentation. Volatile monitoring, so understanding volatiles and how the sampling process itself impacts their natural state on the surface is really important. Understanding the impacts of the sampling process itself on sample collection can only be really measured in situ. In-situ geophysical payloads are specifically referring to collecting geophysical data during traverses to characterize regolith structure and the diversity to facilitate geologic characterization, and geotechnical and physical characterization, like bulk density, porosity, relative density, compressibility, shear strength, and permeability. Those are all things that are really important as we start looking to a future of doing actual large-scale civil engineering on the moon, as we do industrial scale ISRU extraction. Next slide, please. So in the 15 seconds I have left, there is a recommendation here. So the report is very strongly, I wouldn't say endorsed, but it did point out that sample collection and in-situ measurements need to be carefully choreographed to maximize science return, and there are significant benefits and synergies in using in-situ handheld tools to prioritize samples selected for Earth return and understand the impact of sampling on the volatiles we may or may not be collecting at any of these locations we're considering, as well as enhancing collection and curation and providing ground truth for orbital remote sensing data sets. So the other key part of it is also to make sure that in-situ imaging and assessment capability is available to crews during EVA to document their exploration and help facilitate science interpretation of the data after the mission is complete. So that's a great spot to close. That's my last slide. So thanks very much.